so far we have done a lot of stuff. Okay, we have already covered different kinds of graphs. We have covered graphs. We have covered different concepts in the graph: tree, links, cut sets, loops and fundamental loops, cut sets, fundamental cut sets. Right? These are things that we have covered. And then from this, what we did was from the fundamental cut set method in the previous lecture, we built up the incidence matrix first. We went ahead and built up an incidence matrix. We found that the incidence matrix was linearly dependent. Then we cancelled out, or we assigned a node to ground or datum, and then we found that the reduced incidence matrix was linearly independent. Good. Then what did we do? We used this linear independence. We also looked at we also derived Telegans theorem, right? We also worked out all the different branch voltages, found that the matrix corresponding to the this particular equation is A transpose. A transpose times E is equal to V, right? And we proved that this is indeed A transpose. Fine. And then we proved Telegans theorem. Telegans theorem basically said that V transpose times I is equal to 0. In other words, the dot product of the voltage vector and the current vector is equal to 0. In other words, the voltage and current vectors are orthogonal to each other at 90 degrees with respect to each other. Fine. This is something that we proved in the previous class. And Telegans theorem has far reaching ramifications, right. One of the ramifications, one of the special cases is law of conservation of power, energy, right. That is total power in the circuit is going to be equal to 0. That is one of the many ramifications, that is a special case. Fine. But otherwise Telegans theorem, we are going to see that we are going to use it from time to time, we will pull it up. Okay. After this, what we did was, we are not really that keen about all these nodes and so on. So, we came up with this node voltage method of analysis, right. So, we did the node voltage method of analysis. First, we worked on the node voltage method only with current sources. It was quite straightforward with only current sources. Then we changed some of the current sources. I think one of the current sources was changed to a voltage source. There we introduced the super node concept, right, where you merge the two nodes and draw a Gaussian surface around the two nodes, and then you write a single node voltage equation for that joint node, right. So, this is what we saw in the previous class. Now, the node voltage method uses only KCL, right. You are basically repeatedly writing KCLs, right. As many nodes there are, you are writing that many KCLs. That is the node voltage method. KVL is implicit, right. You are never really going to write KVL, but KVL is implied in the node voltage method. How is it implied? How is the KVL implied? You are considering potential difference. You are saying that the branch voltage across, let us say R7 is V2 minus V0. Okay. That itself is a reflection, that itself implies a deep understanding of KVL. Fine. So, you are not really going to write KVL, KVL is implied in your analysis, you do not have to worry about KVL. Done. So, this is the node voltage method. Now, we are going to move on. So, node voltage method was an extension of the fundamental cut sets, right. Instead of writing KCLs for the fundamental cut sets, you said let me make it easier, I am going to write KCLs for every node except one node, which is the ground node. Okay. Understood? All right. So, the next method that we are going to study, this is called the mesh method. This is an extension of what? Fundamental, which one? Loops, right. That one was using cut sets, this is going to use loops. All right. So, this is an extension of fundamental loops. Fundamental loops is not that straightforward, you have to think of the graph, you have to think of the tree, then you have to pick up the loop, the links, and for each link you have to build a fundamental loop, right. So, a lot of work was involved. Here we are bypassing all of that work, but this is basically at the heart of it, it is the same thing that you are going to do at the heart of it. Okay. Then in the previous method you wrote only KCLs, here you are only going to write KVLs. So, whenever you think of loops, you are going to write KVLs, you are only going to write KVLs. And what about the KCLs? They are going to be implicit. Okay. So, the KCLs we are going to imply them, they are going to be implicit in the setup. Somehow the way we are going to set things up, KCL is going to be automatic. So, we will not write any KCL, KCL is automatically going to be satisfied. Fine, this is the plan. Okay. So, let us do by example. Okay. So, consider this circuit, quite horrible. How many branches, how many nodes are there? I have numbered the branches, right. V1, V2, R1, R2, V1, V2, R3, R4, R5. How many branches are there? Branches, as many components, 11 branches, right. I have, it is all numbered 1, 2, 3, 4, 5, 6, 7, all the way to 11. Huh? How can there be 10 components? I forgot R4. Okay, let us throw in one R4 over here. All right, fine. So, Okay. So, since I have forgotten R4, this number of branches now becomes 10. Great. And number of nodes? 9. I see only 7 nodes. Huh? Only 7 nodes. So, how many elements in the tree? 6 elements in the tree. How many links? 4. How many fundamental cut sets? 6. How many fundamental loops? 4. Okay. Now, what you are going to see is that the fundamental loops 4, you can already see the fundamental loops. Okay. One loop is this one, this is a second loop, this is a third loop, and this is a fourth loop. All right, they are there visually, they are already there, you can see them. So, instead of thinking about the tree and the links and so on, I say, or what the mesh method does is, you directly declare that these are the 4 loops we are going to work with. Okay, let us not worry too much. These are going to be the 4 meshes. Okay, so this is the mesh method. So, we are going to call these 4 meshes. And what we are going to do is, for each mesh, we are going to define a mesh current. All right, I1, I2, I3, I4. These are the 4 mesh currents. Now, what is the current in R3? What is the current in R3 left to right? I2. What is the current in R5 left to right? I3. Very good. What is the current in R7 left to right? Left to right R7. I1 minus I2. Why? This is correct. Basically, this is the logic, this is the way you are thinking, and this is the right way of thinking. Okay, this is exactly the way I want you to think. Okay, that there is some sort of an overlying mesh current, right. It is not really a thing, the mesh current is not really a thing, but finally the individual mesh currents are deciding what is going to be the current in the elements in between. Fine. However, the actual reason why this is happening is as follows. So, if this current is I2, this current is I2, right? Yes. And what is this current? I1. Okay. Then you do a KCL, what is this current? I1 minus I2. So, the actual reason why it is I1 minus I2 is that KCL. Okay. But we are not going to think of KCLs at all. Our strategy is, do not think about the KCL, you are going to deal with these meshes, and the meshes will imply that you already know KCL. You have got all the KCLs in the bag, you do not have to do anything. Okay? This is the plan. So, this is how KCL is implicit. Fine? We said earlier KCL is implicit. This is what we are going to do. We are only going to write K VLs. How many KVLs are we going to write? 4. And by now you have understood the way I do things. Okay. When I have to write 4 KVLs, I am going to write it up in the form of a matrix with 4 rows. Let us make it a little bigger. Okay. Now, how many unknowns are there over here? Which are the unknowns? I have written the unknowns in small letters. Which currents? The mesh currents I1, I2, I3, I4. These are the 4 unknowns, and only these, because if you know these 4 currents, you know all the currents, and if you know all the currents, then you know all the branch voltages also. So, the knowledge of just these 4 unknowns I1, I2, I3, I4 is sufficient for you to solve the circuit. You can do the rest, there is nothing much left. Fine. So, I1, I2, I3, I4 are the 4 unknowns. How many rows, how many columns in the matrix? How many rows are there? 4, because there are 4 KVLs. How many columns? How many columns? Louder? Why 6? There are 4 over here, no? So, this will be how many? It has to be 4, it can't be 6. Okay. So, it is a 4 by 4 matrix that we are working with. All right. Now, let us look at mesh number 1. We do it in order, and we are always going to follow the arrow that we have drawn. We have drawn 4 mesh currents with 4 arrows. Okay. So, we are going to follow those arrows. What is KVL? What is the statement of KVL? The sum of potential drops along a loop is equal to 0. So, along this arrow we are going to go with potential drops, and we are going to add the potential drops to 0. Fine. This is KVL. Okay. So, we start with the voltage source V1. Which loop am I working with? This is the one I am working with. Okay. And I am going to start first with V1. What is the drop? Minus V1 is the drop. Fine. It is a raise of V1. So, it is not a drop, it is a drop of minus V1. Then what is the drop going from left to right across R7? I1 minus I2 times R7. What is the drop going from top to bottom across R9? I1 minus I4 times R9. What is the drop from right to left across R10? I1 R10. Okay. Sum of all these drops is equal to 0. Very good. So, let us write it up. First, I am going to do the voltage source. Minus V1 is the drop, and minus V1 I will move to the right hand side and write it as plus V1. Then I have I1 minus I2 into R7. Then I have I1 minus I4 into R9, and lastly I have R10. Is this clear? Are you able to do this mentally? Clear? Okay. Go to the next loop, I2. Next loop corresponds to I2. This is very similar. Okay. Drop is now how much? Minus V2. So, we take it to the right side and make it V2. Then I2 goes through R3, R6 and R7, minus I3 goes through R6 and minus I1 goes through R7. Is this okay? Clear? Third equation. Let us go to loop I3. I3 goes through R6, R5 and R8. Minus I4 goes through R8 and minus I2 goes through R6. Fine. And then the last one I4. I4 goes through R8, R4 and R9. And then minus I4 goes minus I1 goes through R9 and minus I3 goes through R8. Fine. Was this easy? Hard? What was it? Easy? Easy. Easy? Okay, good. Because this is supposed to be easy. It's not supposed to be hard. All right. So, you are writing all of these equations in one shot, and then what is the next step after this that a computer has to do? Yeah, inverting the matrix is the job of a computer, you leave it to the computer, and then after that calculating individual branch voltages, individual branch currents you are going to do based on what the computer tells you is the answer for I1, I2, I3, I4. Are we clear? Okay, good. Now, what we are going to do is we are going to make life a little difficult by changing some components. Okay, first what I am going to do is I am going to change that voltage source to a current source. Okay, just for fun. Now, the mesh method relies on writing KVLs. Okay, and if you have a current source, the voltage across the current source is indeterminate. You do not know what is the voltage across a current source. Just like you can't do a KCL when there is a voltage source involved, you can't do a current source when there is a current source involved. Okay. So, the KVL corresponding to loop number 1 is gone. I just can't do it. Fine. Any questions? No. But loop number 1, what is the current? Mesh 1? The current in mesh 1 is capital I1. Okay, so there is nothing to do really, right? You lost one KVL, but you did not need it any which ways. Alright, why did you not need it? Because that answer was readily available. It was capital I1 any which ways. Okay. So, this is how it is. So, that equation is no longer required, right. That current is no longer an unknown. So, the number of unknowns has decreased. So, which are the unknowns now? I2, I3, I4 are unknown. Capital I1 is not unknown any further. So, now my matrix is going to be 3 by 3. Okay, let us do it. So, we go to I2, mesh I2, mesh I1, nothing to be done, and you can't do a KVL any which ways. Mesh I2, again once again we are looking at drops, voltage drops. So, the voltage drop first across the voltage source is minus V2, then the voltage drop across R3 is I2 R3, then the voltage drop across R6 is I2 minus I3 times R6, then the voltage drop across R7 is I2 minus capital I1 times R7. What do I do with the I1? I move it to the right hand side, okay, because it is a known quantity. Fine. Okay. Next, I3 nothing changes, or does it? Nothing changes, it is the same old. Okay, nothing changes with I3. Next, we go to I4. I4, so let us start with R8. So, the drop across R8 is I4 minus I3 times R8. Then the drop across R4 is I4 R4. Then the drop across R9 is I4 minus capital I1 times R9, which is basically I4 R9 minus capital I4 R9. Fine. I moved capital I4 R9 to the right hand side because it is a known quantity. Fine. Next, I1, sorry. Thank you. I1 R9. Fine. Next step would be to invert the matrix, palm it off to a computer. Step after that will be to find out whatever branch voltage, branch current, whatever is required. Once you know I1, I2, I3, in this case I2, I3, I4, you can find out all the branch voltages, all the branch currents. So, those are subsequent steps which we are not going to worry about. Fine. Okay. Let us complicate matters further. Okay. So, what I am going to do is, I am going to remove this R6, okay, and instead of R6, I am going to call it capital I6. Fine. Now, what do we do? So, KCL for loop 1, KVL for loop 1 is not required, loop 1 is fully solved. Okay. KVL for loop 2, mesh 2 cannot be done because there is a current source involved. KVL for mesh 3 cannot be done because there is another current source involved. KVL for mesh 4 is fine, no problem. Okay. So, what do we do? What do we do about meshes 2 and 3? We can merge them. So, that is the strategy, alright. So, when you see that you can't, just like this is just like we did in the node voltage method case when we had voltage sources. Okay. So, when you see there is a problem over here and you can't write the KVL anymore, then you say that let us merge the two KVLs. Okay. So, you merge the two meshes and you are now going to call this a super mesh. Okay. It is the merged thing between the two meshes. Fine. So, now let us look at it once again. What is going to be the current in R3, or what is going to be the current in V2? Let us first call this, label this. What do you want to label this? I2? Let us label it I2. This mesh current is I2, small I2. Okay. What is the current in V2? Going bottom to top? What is the current in V2 going bottom to top? I2. small I2. What's the current in, are you sure it's I2? Okay. But let us define that to be I2, alright. In which case we are going to have another mesh like this, additionally a second mesh which has a value of capital I6. Okay. Now, once again, what is the current through V2, bottom to top? I2. What is the current through R3, left to right? I2. What is the current through R5, left to right? Capital I6 plus small I2. What is the current in R8, right to left? Okay. So, it is I2, small I2 plus capital I6 minus small I4. Fine. Is it clear? Great. Because now we are in place to write out the, how many KVLs should we write? 2 KVLs, not 1. We have 2 KVLs to write. Okay. There are, we have I4, I4 is unknown and I2 is unknown. Okay. So, we have 2 KVLs to write. Okay. So, let us start with I2, the super mesh. We start with the voltage source, drop is minus V1, which I move to the right hand side and it becomes a V1. Then the drop across R3 is I2 times R3. Then the drop across R5 is I2 plus capital I6 times R5. Fine. Is it okay? Then the drop across R8 is I2 plus capital I6 minus I4 times R8. Plus the drop across R7 is I2 minus capital I1 times R7. That completes the loop. Done. Next mesh is the one for I4. So, I go to I4 and let us start with R9. So, the drop is I4 minus capital I1 times R9. Then we have R8 And what is the drop across R8? I4 minus I2 minus capital I6, the whole thing times R8. All right. And last one, R4. What is the drop across R4? I4 R4. And we are done. Is this okay? Understandable? Easy? Not too hard? Not too hard. Very good. Shall I complicate matters further? Yes. More complicated? This is okay? Fine. Okay. Bring it on. Huh? Okay. Let's do something different. Okay. So, I have reduced the mesh size. I have made it 3 meshes only, but I have placed a controlled voltage source. Okay. Okay. So, this is a new circuit. And what do you want to use? Node voltage method or mesh method? So, before you make this choice, whenever you have a choice, suppose somebody gives you a choice, offers you a choice, then you should check how many branches, how many nodes, how mesh, if I used mesh method, how many equations, and if I used node method, how many equations. Okay. So, you should always check this first before you make up your mind and say I will go with this. All right. So, for example, in this case, how many branches are there? R1, R2, R3, R4, R5, 5 resistors and then 3 sources. So, 8 branches. So, B is equal to 8. Okay. Number of meshes is 3. So, N has to be equal to B minus n minus 1 is 3. Okay. I haven't counted the nodes. You can count the nodes, but what I am suggesting is I can see that there are 3 meshes. So, B minus n plus 1 has to be equal to 3, and therefore, B minus n has to be 2. In other words, n has to be 6. Can you check that there are 6 nodes including ground? So, ground and 5 more, is that right? So, I have ground, node 1, node 2, node 3, node 4 and node 5. Okay. It's okay? Yeah, because sometimes counting the nodes becomes difficult. Okay. So, if you use node voltage method, how many equations? 5, out of which how many are voltage sources? So, you expect to write 3 equations if you use the node voltage method, right. 2 equations you can't write. And if you use the mesh method, how many meshes? 3 meshes, out of which how many are current sources? 1. So, in this case it just so happens that the mesh method wins, alright. So, you would rather use the mesh method than the node voltage method. You want to always use the method with the least number of equations. If there is a tie, then it is a toss up, whichever is your favorite, but if it is not a tie, you should always go with the easier one. Why would you want to work harder? Okay. So, let us do the mesh method. So, this mesh, it is a very trivial mesh. How much is the current in this? Capital I6 is the current in this, trivial. We are not going to do anything. Okay. Next one, let us call this small I1 and let us call this small I2. Fine. And we expect a 2 by 2 matrix times I1 I2 to be equal to something. This is how it is going to appear. Fine. This is the plan. Great. Now, before I proceed further, you have over here a controlled voltage source, alright. So, this controlled voltage source is being controlled by a voltage Vx, but what is the value of Vx in terms of our unknowns? What is Vx? How much is Vx? Note the plus minus of Vx. I1 minus I2 times R3. Okay. So, keep this on standby at the back of your mind. So, this is there on the back side. So, whenever we have to call Vx, we know that Vx is nothing but I1 R3 minus I2 R3. Alright, great. Now, let us start our loops. We have only 2 loops to work with. So, the first loop is the loop for I1, right. Let us go start with the voltage source, drop across the voltage source is minus V7, which moves to the right hand side and becomes a plus V7. Then the drop across R3 is I1 minus I2 times R3. Then there is the drop across R4 and R5, which is I1 times R4 and I1 times R5. Excuse me. Done. This is the first loop, seemed fairly easy. The next loop, we are going to start with the voltage source. What is the drop across the voltage source? Minus kVx. Okay, minus kVx is the drop across the voltage source. But what was Vx? Vx is what is already saved for us. So, it is minus k times I1 minus I3 times R3. In other words, it is minus k times I1 R3 plus k times I3 R3. Is this okay? Is this okay? Next, drop across R1 is I2 R1. Next, drop across R3 is I2 minus I1 times R3. Next, drop across R2 is, what is the drop across R2? I2 R2 minus I6 R2. That is it. What do you notice? This is done. This is it. What do you notice about this matrix? It is not symmetric, whereas all of my previous ones, this one was symmetric, the one before that was symmetric or not? Symmetric, the one before that was also symmetric. So, everything earlier was symmetric, only this one is not symmetric. What is going on? What is your conclusion? Whenever you have these controlled sources, symmetry in the matrix is going to break. Okay. If your circuit does not have controlled sources, then the matrix is going to come up symmetric. As soon as I throw in some controlled sources, the symmetry is going to break. Okay. However, if I make k to be equal to 0, if the value of k is equal to 0, then the matrix again is symmetric. Notice, I just plug in k equal to 0 over here, this becomes symmetric, right. These two are symmetric. If I, okay. So, if k, the controlled source voltage, if I make it 0, proportionality constant. If I make it 0, then immediately symmetry comes back. Fine? Question? No? All right. So, we have done quite a bit of the mesh method. All right. By now, you should be able to now solve any circuit. Okay. We have done the node voltage method, we have done the mesh method. You should be able to solve any circuit which has voltage sources, current sources, controlled voltage, controlled current and resistors. So, you should be able to solve any circuit. Okay. What I can guarantee to you is that with the help of this, you now know how to solve DC circuits, circuits with resistors and voltage sources, current sources, controlled voltage and current sources in the most elegant and efficient manner. That much is guaranteed. Okay, you will be able to efficiently solve circuits. Okay. So, those days are gone, the JEE days are gone, right. Do not do that KVL, KCL anymore. Now, you only write mesh method or node method, you have to choose, right, and you have figured out how to choose between mesh and node. All right, you choose based on what is more efficient. Okay, sometimes mesh will win, sometimes node will win, whoever wins you choose that one, right, and then in the most efficient way you will be able to solve circuits. So, this much we have done, fine. All right. Now, we move to the next phase in which we are going to start now, right. So, in the next phase we are going to talk about network theorems. And the first network theorem we have already proved. Which one? Telegan's theorem. We have already proved, we have already understood. What have we understood? We have understood that dot product of all the voltages and currents of, as long as the graph of the circuit is the same, right, V dot I is equal to 0. That is Telegan's theorem. So, Telegan's theorem is already done. The next one on our list is called the reciprocity theorem. Fine. And the reciprocity theorem is going to be proved with the help of Telegan's theorem. We are going to use Telegan's theorem to prove it eventually. But for now, let me just start. What we are going to do is, we are going to start with the problem statement. What is the statement of the theorem? Let us see if you can understand the statement first. So, I have a black box, all right, inside which there are lots of circuit components, hundreds, thousands, millions of circuit components are there. Fine, black box. We do not know what is the connections, what are the connections inside. We do not even know what is inside. Okay, all that we know is that this is a box. Fine, and from the box, two pairs of wires are sticking out. So, these pairs of wires, so whenever you have a pair of wires, we call it a port. Okay, what is a port? What is a port? Pair of wires sticking out. Okay. So, you have a pair of wires coming out, that is called a port, and you can dock things to the port, right. You can have you can do from a port, what can you do? You can dock a ship at a port, right. Then you can do things, right. You can interface, you can import some things from other countries, you can export, import, all this happens at a port, right. So, the same thing applies over here, right. You can have something from outside coming in over here, some current from outside can come in, or you can apply a voltage from outside over here, or this voltage can be applied to something outside, or this can push some current outside, right. So, that is why this is called a port. Fine. Now, this circuit has this box that I have, this has two ports. So, we call it a two port network. Fine. And we are going to label the two ports as port 1 and port 2. Fine. It is just like country with two ports, right. One at Bombay, the other at Madras, something like that. That is called a two port network. So far so good? All right. What is inside the two port network? We do not know. Okay. Now, we are going to make some qualifications in this, because the reciprocity theorem is valid only in certain cases. Okay. It is not valid all the time. When is it valid? It is valid when the two port network contains linear components only, okay, and passive components only. Linear and passive components only. What does that mean? What components are there? Can we be more specific? R, L, C and M. These are the four kinds of circuit elements that are allowed, nothing else is really allowed. Okay. We can't have voltage sources, batteries, current sources, controlled voltage sources, right. All those are not allowed inside this. Diodes, transistors, not allowed. Okay. Now, this is the background of the reciprocity theorem. Now comes the statement. The statement has two parts. I will state it very slowly, right. I will describe it very slowly. The first part is as follows. I am going to take this two port network home and do the following experiment. I will apply a voltage source at port 1, call it V1, and at port 2 I am going to use an ammeter to measure the current. Okay. What is an ammeter? Is it an open circuit or a short circuit? Short circuit. Open circuit. Short circuit. Why? Can it be an open circuit? No, because no current goes through an open circuit. What is there to measure, right? Ammeter will have to measure current. So, it is a short circuit. What about a voltmeter? Voltmeter has to be an open circuit. Why? Can it be a short circuit? No, because short circuit means voltage across is 0. So, the voltmeter will measure 0. I mean, voltmeter has to measure the voltage, right. It can't just short the two voltages. Okay. So, an ammeter is always a short circuit, voltmeter is always an open circuit. I mean, in practice they try to be. A real ammeter, a practical ammeter can't really be a 0 ohm path, but it is going to, at least that is the wish, right. You want it to be as close to 0 as possible. Okay. So, I am still on the statement. of the theorem. It is going to take me a while to state the theorem. So, just go with me. So, you got this 2-port network, you applied V1 at port 1 and with an ammeter you measured I2 at port 2, fine. Next, you dismantle this and you take this 2-port network and apply V1 at port 2. Okay. So, the statement of the theorem says that now if you place an ammeter at port 1, you will get the measurement I2. All right. This is the statement of the theorem. I have not written down the theorem over here, okay, but I need you to understand what is going on. I buy a 2-port network. 2-port network is linear passive. It has only R, L, C, M inside. I bring it home. First, I apply voltage V1 at port 1 and I take an ammeter and measure the current in port 2. Basically, short circuit current in port 2 is what you are measuring and you call that I2. Next, you dismantle this ammeter ammeter and voltage source. You take this voltage source and apply it at port 2, right. You apply V1 at port 2 and the theorem says that now the short circuit current at port 1 has got to be nothing but I2. Clear? Statement of theorem is clear? All right. This is only half. This is the second half. The second half is as follows, that I could also apply a current I1 at port 1 and with a voltmeter let us say I measure V2 with a voltmeter. A voltmeter is open circuit. Okay. So, with a voltmeter I check the voltage across port 2 and I find that it is V2. Okay. Then the theorem says that now if I apply the same current source I1 at port 2 instead of port 1, then I will measure exactly the same voltage V2 at port 1. Is the statement of the theorem clear? Absolutely clear? Okay. Okay. We have a little bit of time, let us try to prove. So, the way we are going to prove it is with the help of Telegan's theorem. Okay. And I am going to make a list of all the voltages and all the currents in experiment A, and I am going to make a list of all the voltages, all the currents in experiment B, and I am going to prove that this measurement, let us call this measurement I x. Okay, I am going to prove that I x is equal to I 2. Fine, all right. And similarly, I will measure all the voltages, all the currents in experiment C, all the voltages and currents in experiment D, and I am going to prove that V x is equal to V 2. Okay, this is the plan. Let us do it step by step. So, A, okay. So, first of all, in circuit A, I have the voltage V 1, okay, across port 1, fine, and let us call this current I 1, I 1 A, fine. I do not know what it is, let us call it I 1 A. Every component that I have, I want to find out the voltage, I want to find out the current. That is the plan. Over here at port 2, what is the voltage? Across the ammeter, what is the voltage? 0, and the current is I 2. This is I 2. Fine. Inside the circuit, inside the 2 port network, let us say there are only resistors L, C, M, let us forget them. Okay. We will think about those later on, much later, many classes down the line, we will think about those. For now, ignore. Okay. They are easy to handle. If you can do resistors, you can do everything else. Let us assume. So, let us say there are all these resistors R1, R2, R3, R4, R5 all the way till Rn, okay, lots and lots of resistors. So, and let us say that we are doing experiment A. So, I R1, I R2 all the way till I Rn, these are all the currents. Okay, I do not know what they are, but let us say this is what they are. What will be the corresponding voltages? R1 into I R1, R2 into I R2 dot 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 Rn into I Rn. Very good. Fine. Now, let us move to experiment B. In experiment B, component by component, we are going to look at it in the same order. Okay. So, in the same order, same polarity. So, where earlier there was V 1, what is now the voltage in experiment B? How much is this voltage? 0, this is an ammeter, and this current is I x. Fine. Earlier where there was I 2 or where there was the ammeter, What is now the voltage and what is now the current? V1, and the current I really do not know. Let us call this current something I, what do you want to call it? I1B. Okay. All right. Now, the resistors inside the box. There are lots of these resistors inside the box. Let us call them, oh, we need to modify our earlier one, IR1A, IR2A, IRNA. Let us put another A subscript. Okay. Fine. And in this case, let us call these currents IR1B, IR2B, dot dot dot, IRNB, and therefore, the corresponding voltages will be R1 times IR1B, R2 times IR2B, dot dot dot, Rn times IRNB. All right. This is our list. Now, what we are going to do is, we are going to apply Tailligon's theorem. Okay, what does Tailligon's theorem say? That as long as the graph of the circuit is the same, is the graph any different between experiment A and B? The circuit has the same graph. Okay. In one case, I had a voltage source over there and an ammeter at port 2, and in the other case I had a voltage source at port 1, sorry, port 2 and ammeter at port 1. I just interchanged the two components. Graph of the circuit is exactly the same. Alright, this is the premise of Tailligon's theorem. So, I can apply the voltages, I can do the dot product of voltages of circuit A, of experiment A, with currents in experiment B. I could also do the dot product of voltages of experiment B with currents in experiment A, and both of these dot products are going to be equal to 0. Fine. So, what do I have? I have the following: V1 times Ix plus, so I am multiplying this one with this one. Okay, V1 times Ix plus 0 times I1B plus R1 times IR1A IR1B plus R2 times IR2A IR2B plus dot 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 plus Rn times IRNA IRNB is equal to 0, and this is also equal to the dot product of these two. What is the dot product of these two? I1A times 0, which I do not need to write. Next, V1 I2 plus R1 times IR1B times IR1A plus R2 times IR2B times IR2A plus dot 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 plus Rn times IRNB times IRNA. And what do you see? just ignore the equal to 0 part, right, that is really not that important, right. What is important is that this whole thing is equal to this whole thing, and all those junk terms they cancel out from both sides, and what are you left with? You are simply left with I x is equal to I 2. Fine. Any questions? This is how you apply Telegon's theorem. You always make a list, list out all the voltages, list out all the currents, be as systematic as possible, then only it will work, right. If you interchange signs, you do some, you take current this way and voltage that way, it is not going to work. Okay. All the branch voltages, all the branch currents have to follow the same convention, correct. Topology matters. Then you list out all the voltages, all the currents in experiment 1, and then in experiment 2 list out all the voltages, all the currents, then you do dot product, then you do dot product. Okay. All the dot products are going to be equal to 0, and what is, I mean, whenever you are applying Telegon's theorem, what you really have to do is do the mixed dot product. Okay. The self dot product equal to 0 is not going to get you very far. The mixed dot product is always going to be helpful. Okay. Voltage of one experiment dot product with currents of the second experiment, and voltages of second with currents of the first. Fine. This is how you apply Telegon's theorem. The second part of the proof is just the same. C and D, can you do it yourself? Can you prove Vx is equal to V2 is equal to, sorry, Vx is equal to V2, can you prove with the help of Telegon's theorem? Just like the same as what we did, just the same, just that here you have to think of a component. So, this is a component called a voltmeter, and you have a component called a voltmeter, that is all. Okay, there is a physical component over there called a voltmeter, right. Topology of the circuit remains exactly the same in both cases. So, you apply Telegon's theorem, list out all voltages, all currents here, list out all voltages, all currents here, and then mix them up, do the mixed dot product twice. Okay, that will automatically give you Vx is equal to V2. So, do this yourself, I do not want to prove it, it is exactly the same proof. Okay, so thank you, let us stop here.